Okay, so we've seen both versions of the improper integrals, the version of integrals over unbounded intervals and the version of integrals for unbounded functions. And it turns out that what we did so far of actually calculating them, in many, many cases, it's not easy. It's not easy not easy or even impossible. Not easy to find the limit or not easy to solve the integral or both. And what we are going to have is some theorems that in some cases actually tell us whether the integral converges or not without calculating it. Determines convergence without actually calculating. And here's the first of those theorems. And it's called the comparison test. That's the name of the theorem. And it says the following. Let f and g, two functions, be non-negative. This is crucial. I'm going to emphasize this because this is one of those, there are several places in the course where mistakes are very, very, very common. This is one of them. Using this test for not necessarily non-negative functions. So they have to be non-negative. Let me emphasize it even more. Tell me when you think it's emphasized enough. You think it's emphasized enough? No? Nice. Okay. So, non-negative. Let f and g be non-negative on an interval of the form on a infinity. And we're going to assume that, maybe I'll write everything, and integrable on a m for every m. Okay. Also, assume that g is greater than or equal to f and greater than or equal to 0. This is thus just emphasizing this fact even again. For every x greater than or equal to a. Then, and let me draw the picture before I actually write the result. So the picture is this. Here's a. There's infinity. Do you see it? And we have two functions. One, we call it g. Looks something like this. This is g. And I'm going to assume in a second that the integral of g from a to infinity converges. And f lies between g and the x-axis. So f here in orange is something like this. What can we say about the integral of f? It has to converge as well. Do you agree? It's kind of a sandwich-like argument, in a sense. Do you see that? If the integral of g converges, if the area under the graph of the blue function is bounded, well, the area under the graph of the orange function is going to be bounded as well. And vice versa, if the area under the graph of the orange function diverges, then of course the area under the graph of the blue function is going to diverge as well. Let me write that. So then, the integral from a to infinity of g converges implies the integral from a to infinity of f converges. And it's, of course, 2 for the price of 1 theorem. So if this does not happen, then, of course, this does not happen. So if the integral from a to infinity of f diverges, this is not another theorem. It's just a different way of saying the same theorem, then the integral from a to infinity of g diverges. Clear? Do you see why it's crucial that the functions are not negative? If you allow, for example, f to take negative values, f can just be something like going all the way down here. And although the area under G can be finite, the area under F can be minus infinity. Do you see that? So that's why this is crucial. Yes, question?
We could say that they're both only negative too.
Right. You could, that's true. Good remark. You could apply this theorem when both are non-positive. Just take their minuses, do the theorem, and then take the minuses again. That's true. But they cannot change signs. They have to be on the same side of the x-axis. Okay, I'm not going to prove the theorem. I think the drawing is rather convincing. Do you agree? But I am going to do examples. That's important. So example, what was our last example number? 7. So this is 8. Yep. So example 8, suppose we want to do the integral from 1 to infinity of dx over x squared plus 5x. And we don't want to calculate it. We just want to know, does this converge or not? Okay? Now I want to show you, before I actually write the formal solution, I want to tell you how I think about this. The way I think about this is the following. When we go towards infinity, this is only intuition. I'm not going to write this. I'm going to write the formal stuff. This is how I'm thinking. As x's get bigger, which is the dominant factor here? X squared. Do you agree? X squared, for x equals 1,000,000, 1,000,000 squared is by far bigger than 5,000,000. Do you agree? So x squared is the one that actually determines the behavior of this thing. In other words, this behaves like 1 over x squared in terms of convergence. Do you agree? And what does 1 over x squared behave like on 1 infinity? It converges. Why? Right, because of the theorem that I didn't erase, namely this theorem. Look here a second. The integral from 1 to infinity of 1 over x to the power 2 converges, because 2 is greater than 1. Is the intuition clear? So now I want to write it formally. I can't just write this behaves like, because behaves like can have many meanings. I have to formalize it, and the way to formalize this is the theorem. So, for x greater than or equal to 1, those are the x's I'm dealing with, 1 over x squared is greater than or equal to 1 over x squared plus 5x, which in turn is greater than or equal to 0. Because here the denominator is bigger, so the fraction is smaller. Does everybody agree to this? Okay. So I'm in the setting of the comparison test. I have f and g, or which was the bigger? G and f, both are positive when x's are greater than 1, and one is bigger than the other. By the comparison test, the integral from 1 to infinity of dx over x squared plus 5x converges. Why is that? Since the bigger integral converges as well. Since the integral from 1 to infinity of 1 over x squared converges. This, by the way, we know by previous theorem. Clear? And note, this is important. The comparison itself is at the level of the functions. The result is at the level of the integrals. So I conclude about the integral, but the comparison itself is at the level of the functions. I cannot compare the snakes because I don't know that they exist yet. Okay, and that's also a common mistake in this context. Questions on this? Everybody good? Okay, remark. Let's write it here. Remark. We can rephrase the theorem not for a to infinity intervals, but rather for unbounded functions. So a similar theorem for unbounded functions. Okay, what would it look like? I don't want to write everything again. So again, it would be let f and g be non-negative on a, b open, and integrable on a, b minus epsilon, just like before. Assume that g is greater than f pam, then the integral from a to b, which is improper now in the sense of the unbounded function, converges, imply the integral of the smaller one converges. Well, almost similar. Okay, good? Let's do an example of using that. Example number 9 for today. Suppose I want to do the integral from 0 to 1 of the same function we had previously, x squared plus 5x. What's the intuition first? What do I expect? When I look, this is an improper integral of the unbounded function type. This function is not bounded near 0. Which is the dominant factor near 0? Is it the x squared or the 5x? It's the 5x, right? When x is very, very small, x squared is extremely small, and this is the one that sets the tone. Do you agree? So I expect it to behave like 1 over 5x, or like 1 over x, which diverges. Right? So that's my intuition. Formally, for x's between 0 and 1, those are the x's I'm dealing with, x is greater than or equal to x squared, right? When you square something between 0 and 1, you make it smaller. Do you agree? Therefore, I'm going to add 5x to both sides. 6x is greater than or equal to x squared plus 5x. That's what I want. Okay, and therefore, now I want to take the reciprocals. So when I take the reciprocals, I change the direction of the inequality. So 1 over 6x is less than or equal to 1 over x squared plus 5x, and greater than or equal to 0. That's important. So now this is the g, this is the f. We know that this integral diverges, therefore this integral diverges. The integral from 0 to 1 of 1 over 6x diverges. How do we know this? The 6 we can just pull out. It's just a constant. And the integral of 1 over x diverges, again, because of this theorem here that I'm going to leave on the board. The integral from 0 to 1 of the x over x to the alpha converges if and only if alpha is less than 1. When alpha equals 1, it diverges. So this diverges. So, by comparison, the integral from 0 to 1 of 1 over x squared plus 5x diverges as well. Clear? So this is the formal writing. The intuition is good, but it's not formal writing. You have to be careful with spelling out intuitions. Okay. Another version of the comparison test. Again, it has versions for both. So let me write it. theorem. This is called the limit comparison test. And it says the following. F and G as before. F, G, non-negative. You need to emphasize this, right? Non-negative. How many people here are willing to promise that they will never use these theorems for functions which are not non-negative? You're willing to promise? Wow, that's taking a serious oath there. So, from my experience, there are people sitting with us right this minute, looking at all these fireworks, and they're going to do it. It's statistics. You can never argue with statistics, right? Okay, non-negative on A infinity and integrable on ... as before. And now, instead of assuming that one is actually bigger than the other, I'm going to assume a limit version of them behaving the same. Assume that the limit as x goes to infinity of the quotient, the limit of the quotient equals some L, where this L is a number between 0 and infinity. Then the integral from a to infinity of f and the integral from a to infinity of g both converge or both diverge. Loosely speaking, they behave the same. Well, that's not loosely speaking. That's precisely what this is saying. Okay? Example. Oh, good. Let's leave this remark. You can write it again. A similar theorem for unbounded functions. For unbounded functions, it's going to be a similar sort of theorem. What's going to change here is that rather than having x go to infinity, you're going to have x go to b, where the function is unbounded. Okay? That's going to be the difference, and this is going to be the integral from a to b of unbounded functions. Clear? I don't want to spell it out again. Okay? Good? Okay, let's do an example. Example number what? 10. Suppose we want to calculate the integral from 0 to 1/2 of the function 1 over x times root 1 minus x. So first of all, we recognize that there are no infinities here, right? So this is not improper in the sense of infinite intervals. But is it a regular definite integral? No. The function is not bounded. Where is this function not bounded? At 0. Also at 1. Do you agree? When x approaches 1, 1 minus x approaches 0. It's in the denominator. It also explodes. Do you agree? But 1 is irrelevant, because the interval is from 0 to 1/2. So this is an unbounded function only at 0 on this interval. Does everybody see that? Yup? Okay, so we're dealing with an improper integral. We want to determine if it converges without calculating it. What does it behave like? What's my intuition? this factor is bounded. It doesn't contribute to the unboundedness on this interval. Do you agree? So it behaves like 1 over x. Did everybody follow that intuition? Is that intuition clear? The 1 minus x square root is a bounded factor on this interval. Okay? So this behaves like, I don't want to even write that. It behaves like the integral of 1 over x, but the integral of 1 over x, what? Diverges. That's again this theorem. The integral from 0 to 1, and we said that it doesn't matter whether you write here 1 or 1/2 or whatever. The integral from 0 to something of these things converges if and only if alpha is less than 1. When alpha equals 1, it diverges. Right? So this behaves like 1 over x, which diverges. How do I formalize that? I'm going to use the comparison test. Because this factor, root of 1 minus x, on this interval, when x is allowed to range between 0 and 1/2, is a bounded factor. Even 1 over it is bounded. That's what's really important. Okay, so it doesn't contribute to the improperness of the integral. This is what's causing that unboundedness. Okay? So the limit, as x approaches, and this is this remark, the similar version for unbounded functions. So I have to approach the point where I'm unbounded. X approaches 0. Of the quotient of the original function, which I want to compare this one, and the function I'm comparing to, namely 1 over x. This is what I claim it behaves like. Is it clear why I wrote this? Back to the theorem for a second. Where is it? The limit of the quotient of the functions, not when x goes to infinity, when x goes to the point where it's unbounded. That's the other version of this theorem. Good? So what's this limit? This x and this x cancel out, so I get the limit x goes to 0 of 1 over root 1 minus x. And what is this limit? 1. What do I care about? What's the property of 1 that I care about here? It's a number between 0 and infinity. That's all I care about. I don't care what exactly I got. I only care that it has a limit, which is between 0 and infinity. So 1 is between 0 and infinity. That's one condition. The other is that the integral from 0 to 1/2 of 1 over x diverges. That I know from the previous theorem. Together, this implies, by the comparison test, by the limit comparison test, sometimes referred to as LCT, limit comparison test, the original integral diverges as well. This is the original integral. Good? Let me give you a homework problem. Example 11. Homework. Try it on your own. But I'm telling you it's going to be a bit trickier. Okay? A bit trickier. Won't be as smooth as this one. So try the integral from 1/2 to 1 of the same thing. Dx over x root 1 minus x. Same function, different interval. Clear? Try to do this using the comparison test, of course, the limit comparison test. Okay? Okay, good. So these are the comparison tests. the limit one doesn't require to actually compare which of the functions is bigger. In that sense, it's sometimes easier to work with. But both of them have this restriction, the restriction that they only work for non-negative functions. Okay? What if I have functions which are sometimes negative and sometimes positive, which are not of a fixed sign? Well, I have less tools to work with, but still there is stuff I can do. And this is what I want to quote now. So I'm going to start with a definition. We say that the integral from a to infinity of f converges absolutely, or absolutely converges, both are used. This is what I'm defining. If the integral from a to infinity of f in absolute value converges. So we say that an integral, an improper integral, converges absolutely if, when we put the absolute value, we get a converging integral. That's the definition. And a theorem says that absolute convergence implies just convergence. In other words, if you have a function that when you plug it into the integral from a to infinity, take its absolute value, and you see that it converges, that implies that the original function without the absolute value would converge as well from a to infinity, the integral. Okay? But this is not a remark. This direction is false. So it's not true that when an integral converges, it would converge in absolute value as well. So I want to give you an example of this. I want to give you an example of this. But before that, I want to just show you a bit of intuition. Where do these things come from? So what does it mean to converge absolutely? It kind of means, so suppose we have a function, and now I'm going to draw a function that's not necessarily always the same sign, because if a function is always positive, then these two things coincide, right? There's no meaning to it. So let's take a function that looks maybe something like this. Sometimes it's negative, sometimes it's positive. Something like this. And saying that it converges means intuitively, we're now working only on the intuitive level, saying that it converges means that summing the areas all the way to infinity gives us a finite number, right? It could happen that the reason for the converges is cancellation of positive and negative areas. So we have a plus area here, but then we subtract this area, then we add this area, and subtract this, and add this, and subtract this, and add this, and eventually it could happen that the convergence is because of the cancellations. Whereas, if we take the absolute value of the function, which pictorially would just be obtained by flipping all these parts where it's negative, so in orange is the absolute value of the function. Do you agree that this is what the absolute value of the function would look like? In orange. Yep. It could happen that the orange one would diverge. When we're just adding up all these areas and not subtracting half of them, it could be that the integral would diverge. Okay, and we'll see an example where this actually happens in a minute. So I'm not going to prove this theorem. Okay, I'm not going to prove this theorem. The statement is, if the orange one converges, then the blue one would definitely converge. So if you do cancellations, it would definitely converge. That's this statement. However, it could happen that the orange one diverges, whereas the original blue one converges. That's why this is not an if and only if statement. Question? What do you mean, go the other way also? No, there's no such notion of diverges absolutely. Okay? If this diverges, okay, it doesn't imply that this diverges. That's exactly this remark here, that the other way is false. Okay, so the only notion is converges absolutely. Okay, let's give some examples. So example, what number are we on? 12. Example 12 for today. Suppose we want to look at the integral from 1 to infinity of cosine x in absolute value over x squared dx. On the interval 1 to infinity, this is a positive function. Do you agree? It's positive because I just forced the cosine to be positive by sticking it into an absolute value. Right? So this is a positive function. What do you intuitively think it behaves like? 1 over x squared. Do you agree? How am I going to formalize that? Right, with a comparison test. So, here goes. Cosine x in absolute value over x squared. Well, it's non-negative. I'm safe here. And on the other hand, it's less than or equal to 1 over x squared because cosine is always less than 1. Right? On 1 infinity. Does everybody agree to this? The integral from 1 to infinity of 1 over x squared converges. That's our theorem with the alphas. Converges. Therefore, by the comparison test, the integral from 1 to infinity of cosine x in absolute value over x squared converges as well. Do you agree to this? Everybody? Okay. So this was kind of a warm-up towards what I really wanted to write, which is example 13. What about the integral from 1 to infinity of cosine x without absolute value? What can you say about this thing?
Yeah, definitely.
Does it converge?
Yes. Yeah.
Yes. Why?
The absolute value converges.
Right. This we cannot run a comparison test on. This is not a positive, a non-negative function. Do you agree? And if I just put this on the board without everything that precedes it, and somebody would try to run a comparison test on this, it's false. It's wrong. You can't do that. You cannot apply a theorem when its conditions don't hold. Okay? However, you can take the absolute value of this, which is precisely this, and it converges. This we did prove. Therefore, this converges absolutely. Its absolute value converges, and since it converges absolutely by the theorem, which I didn't prove, I just kind of argued it, it converges. Converges absolutely, and thus converges. Clear? Everybody good? Questions? Okay, good. Another example. Oh, I just erased my standard remark, but once again, the term converges absolutely can be phrased exactly the same way for unbounded functions. You just replace the unbounded interval with an unbounded function. Okay, exactly same term. Okay? So everything we say in the context of improper integrals has dual versions. For improper in the sense of unbounded, and for improper in the sense of infinite intervals. Okay, example number 14 for today. Suppose I want to determine convergence of the integral from 1 to infinity of sine x over x. Do you remember what this function looks like? We drew it several times. Mostly we were interested in this function because of its behavior near 0, right? The limit of this goes to 1, and that's what usually we were interested in. But we also know what it looks like as we approach infinity. This is exactly a situation of a kind of sine wave with the amplitude kind of deteriorating as we approach infinity. Do you agree? Okay, and we're looking at the integral, well, from 1 to infinity. So it's not even this, it's something like this. Okay, this is our function. And this is going to be precisely our example. I'm not going to have time to do all the details. I'm not going to have time. But this is going to be our example of a function that converges. This is going to converge, but in absolute value it's not. It's going to diverge. So let me start it, and I'm going to... so next time I'm going to take a few minutes and tie up some loose ends from improper integrals, which I still have to mention before we move on to series, which is our next topic. So I want to calculate this. Here I'm going to actually calculate this, or almost. So this is the limit as m goes to infinity of the integral from 1 to m of sine x over x dx. This is the definition, remember? Okay. And now I want to calculate this. Okay. So on the integral from 1 to m, let's write it like this. Limit m goes to infinity. And now I want to work on this thing. On this thing, this is a regular definite integral, bounded function on a bounded interval from 1 to m. I want to do integration by parts. I can do that. It's a regular, finite, definite integral. Okay? So my parts are going to be, u is going to be 1 over x, u prime is going to be negative 1 over x squared, v prime is going to be sine of x, and v is going to be minus cosine of x. Do you agree that u prime and u and v prime are precisely the factors here? So what do I get? I get the limit of, and here I have u times v, so negative cosine x over x, evaluated between 1 and m. It's the definite version of integration by parts, minus the integral from 1 to m of u prime v. So it's a minus, minus, minus. All in all, we're left with a minus cosine x over x squared. Do you agree? Okay, so I can apply any of the methods I want, integration by parts, substitutions, whatever, as long as I'm working at the definite integral level. Some people actually do these things at the 1 to infinity level. You may even find that in books. Please don't do that. Okay, please don't do that. It's uneducational. It results in plugging infinities into functions, and that's not defined. Okay, so please always do all the theorems at the level of the definite integral. That's rock solid. That's okay. Everything else is kind of shaky. Don't do that. Let's continue this. So what do we have here? We have minus cosine m over m. That's some number. Right? Limit minus cosine m over m minus cosine 1 over 1, so plus cosine of 1, minus this thing, integral from 1 to m of cosine x over x squared, and this is the limit we want to calculate. Do you agree? What does this thing go to as m goes to infinity?
0.
This goes to 0. Cosine m is bounded. 1 over m goes to 0. Bounded times goes to 0, goes to 0. So this thing, move away, goes to 0 as m goes to infinity. This is a constant. What about this thing? Converges. What do you mean by converges? You're right. But what do you mean? What do you mean? This is a definite integral. What do you mean it converges?
By the comparison test?
No, this is a definite integral.
By 13?
By 13 what? You're right, but you have to say it correctly. I'm trying to make you say it correctly.
Which is absolute.
When m goes to infinity, this thing, by definition, gives the integral from 1 to infinity of cosine x over x squared, right? That's the definition of this thing. It's the limit of, as m goes to infinity of this.
Yeah.
And we know that this is a number. We don't know what it is. We know it exists. We prove that this thing converges. It's some number. I don't know exactly what, but it exists. Okay? So all in all, I didn't calculate this limit. I just know that this limit exists. So the limit exists. Hence, the integral from 1 to infinity of sine x over x converges. Okay? And let me add here just a final remark. One can show, and it's not completely straightforward, but if somebody's interested, I will give you the guidelines of how to show it. It's a bit calculations like this, that the integral from 1 to infinity of sine x over x in absolute value diverges. Which means that this is an example, this is the classic example of a function that its integral from 1 to infinity converges, but not absolutely. Okay, when you plug it in absolute value, when you try to take the areas all in plus, rather than canceling them out, plus minus, it diverges. Okay, so if you're interested in solving this, please come up to me later, and I'll kind of give you, I'll just break it up for you into several small intermediate examples, which, when you take them together, give you the divergence of this. You can try it on your own. It's not that difficult, but it may be a bit challenging. Okay. Yeah. So I still have just a bit more to say about integrals, but we're out of time. So we'll start with that next time and then move on to series. Question? Yes.
showing that different than what we did here with cosine?
So the question was, how is that different than what we did here? It's different. I think the key difference is here you have an x squared in the denominator, and that's why this converged. Okay, whereas if you take it with an x, it won't work. So it's not the cosine versus the sine that makes the difference. It's the x in the denominator versus the x squared in the denominator that makes the difference. Okay? Okay, so we continue next time.